Okay, CEA class. We are going to be doing some calculations for your water supply. So we went over in class this PowerPoint presentation. In the presentation, we talked about different water sources. Now, mainly it talked about municipal water sources. So in a town, where they get their water from, how they store it, and how they distribute it, and especially how they measure the pressure in the system and maintain that pressure. Okay. Um, I don't really want to go through this whole PowerPoint again, but I do want to come back and refer to different slides in here as we go. Um, I'm going to assume that you were here for this. If not, I'm going to assume that you read through this and hopefully familiarize yourself with this. So, we are going to be talking, and really where we start. Um, we look at this. This is what we use at the very end of our calculations to convert from what we are using as a measure, unit of measure is feet of water, and we got to convert over to PSI. So we use this near the end. Most of what we do in this little exercise begins down here. We've already talked about distribution of water and all that other stuff. So we want to talk about what head is. So head relates to the energy of an incompressible fluid like water to the height of an equivalent column of fluid. So this pipe full of water will keep this much water suspended in this column. Again, I don't want to get too deeply into that, but we will start our calculations by calculating what we call static head, and that is basically the elevation difference between the water in a water tower and where it comes out of either a water main or a fixture in our house. So the first thing we're going to do, so they give you an example here to figure the static head. So it says, what is the static head at a residential supply line if the water level in the elevated tank is 943 feet and the elevation of the supply line is 890 feet? Well, it literally, the static head is the difference between those. So the difference between those is 53. So that is 53 feet of water. That's how you would express this. It is not, and you have to put the units in there. So that is a measurement of water pressure for us, basically, potential energy, because the gravity will push that water down through the pipes. That is energy. That's work being done. So that is the first thing you're going to do in any scenario that we have. So for example, when we come back, oops, yes, back over. I need to shrink this, I guess. Back over to our activity, the first thing they're going to ask us to do. So, this is an activity. They give you these facts, and we're going to be looking at those here in a second. They give you a map. They say, here is where you're going to, here's your water tower. So, that is 3.12 miles from that water tower to our site. So, we are going to lose water pressure over that distance getting it there due to the friction in the pipe that we have to push the water through. So down here, they want you to A, calculate the static head at the point of discharge under 10th Street. Okay, static head. So here's 10th Street. We got to figure out what the elevation at 10th Street is. We are going to just use um, this measurement right here. So if you see right here, it says 769 feet. We're going to use that as our elevation, okay, of 10th Street. But when we come back down here, it says at the point of discharge under 10th Street. So what are they talking about? It says the elevation of the lowest point of the tower's cavity is this. Do they tell us where we're at under 10th Street? Got, complete the following calculations in your affordable home and engineering notebook. 6 feet. Here we go. I'm sorry. It just took me a second. So the pipe is 6 feet below 10th Street. And we figured out down here we are at 669 feet. So what is 6 feet below 669 feet? It would be 663 feet, right? So if we're 663 feet, we got it. And this is the height of our water tower, we got to subtract 663 from 872, correct? First off, I got to make sure I'm right on this. 763, not 663. So what that's going to look like. So I have in my notebook, this is activity, um, Lord, 2.3.8. So I'm going to come down here and I'm going to say activity 2.3.8. And then I'm going to come click back over here. That's not what I want. That is not what I want. So right here, we are doing number 1A. So I'm going to go ahead and go number 1A. Find static head. And we know that static head is the height of our water tower. So 872.81. And we're going to subtract from it the 6 feet below 10th Street. We figured 10th Street was 763 or 769, I'm sorry, minus another 6 feet. So that's 763 feet. So if we subtract those two, we will have our static head in the form of, so if we subtract these two, that's the height of our water tower, right? Right here. And 6 feet below 10th Street, remember 10th Street right here is at 769 feet. Go another 6 feet down, you're at 763 feet. Okay, so over here, I've written that out. And I'm going to go onto my calculator. I'm going to say 872.81 minus 763, and I get 109.81 feet of water. That is my static head. Okay, so I'm going to come back over here. B says calculate the head loss, including the losses for pipe fittings. So what they tell you in your PowerPoint here is we use a formula. This formula right here to calculate our losses of pressure due to friction in the pipe. Now you can have friction in the pipe in two ways. Friction going down a length of pipe, and then every time it makes a little turn through a fitting, it will have more friction. And so you got to account for all those things. So the first step in doing this is going to be to do the following. Um, we are going to take the first thing into account. We got to turn, because we're going to be using uh, this formula right here that I showed you in the PowerPoint. Length here has to be in feet. Okay, see right down here, length in feet. So we got to convert what we have over here in miles, in miles to feet. So these are what we call major losses, that length. So we're going to come here, and this is going to be 1B. We're going to say major losses. So we take 3.12 and we multiply it by the number of feet in a mile, which is 5,280. So 5,280 times 3.12, and we get 16,473.6 feet. Okay, so we also know that we have a 90-degree seven 90-degree flanged elbows and one 45-degree flanged elbow. So those also take up some pressure due to friction. So what we're going to do is we got to look up our fittings on this chart. And what it'll do is it'll say for this size, for a 6-inch pipe that has flanged fittings, if you have a 90-degree elbow for a six, you got to add 8.9 feet to that length. So they take the friction in that elbow and they equate it to a certain length that we then add to this length, and then we plug that into our formula as the overall length. So we have to equate. So these are called minor losses when we do these fittings. So we're going to say here minor losses, and we have 7 90-degree elbows. And we have, if I go back and look for you, we have 145-degree elbow. So we go 145-degree elbow. So this equals, so we also then got to look at the type of pipe we got here. We have 8-inch cast iron pipe. So then when we come back over here, here's our chart. And we have flanged fittings. That's what they said in there. I'll show you when we get there. So 8-inch flange, we're on flanged fittings, 8-inch pipe. You could tell we have flanged fittings because there is no 8-inch up here anyway. But anyway, 8-inch flange. Here's our 90-degree elbows right here. So for every 90-degree elbow, we have to add 12 feet. And for every 45-degree elbow, we just come down two more. We have to add 7.7 feet. Okay. So what that looks like is you take 7 times 12, and we'll get our feet. This is 1 times 7.7 is going to be 7.7, right? But if we take our 12 times 7, you get 84. We add those together, and you're at 91.7. So then we're going to say total losses. And that's going to be our 16,478 73, I'm sorry, point 0.6 plus our 91.7. So 16,473.6 plus 91.7, and we get 16,565.3 feet. This is our total losses. So we didn't figure out the total losses in pressure yet, but this is the length that we are now going to plug into this formula right there. These other things they gave us, or we can easily get by looking on a chart. So most of this is using this formula and figuring out the length, most of this exercise. So if we go back now, the number 3 says, or C says, so we did this. We figured out the head loss, including the losses for the pipe fittings. So we did major and minor losses and added them together. Calculate the dynamic head at the point of discharge under 10th Street. So I'm going to show you how to do that. So all dynamic head is your static head minus your pressure losses from the friction. That's all dynamic head is. So we're going to come down here and we're going to say C, dynamic head. Okay, but what we have to do first is turn this into the pressure. So we got to plug these numbers here into our formula. So our HF, so we're going to use, I don't want to rewrite this formula. So we're going to find these values. I'm going to rewrite it with, not like this, but with the values in here. So we're going to say HF equals 10.44 times this number right here, 16,565.3 times, and then we got to look here, that is Q. Q is our flow rate. So if we go back, they gave us that, didn't they? I think they did. 100 gallons per minute. That is our flow rate. So times 100. That all gets divided by, oops, I'm sorry, I should have left that up. That all gets divided by C to the 1.85 times D. D is the diameter of pipe. They gave that to us. And this is what I showed you on that chart already. So if I show you the chart, that's this. Now, what kind of pipe do we have? Let's go back and look. We have cast iron that's old. So if we go back and look, here's our cast iron right here. No, I'm sorry. Here's our cast iron right here. This would be a value for the new pipe. This is a value for an older pipe. So 100 is our C. So if we come back here, this is going to be 100. By the way, this is to the 1.85. This is to the 1.85. And that's going to be multiplied by the diameter of our pipe, which is 8 inches times 8 to the 4.85. 1.8655. So now, if we type this into a calculator, we're going to get an answer. That answer then is going to be the amount of feet of water that we have to subtract from this due to the friction losses. So this is basically a measure of pressure right now, potential energy. So we got to type this into a calculator and get an answer, and then that answer we will come down here and we will calculate our dynamic head. Okay? So I'm going to go ahead and pause this video while I go ahead and do this. Now, what I like to do is I'll multiply all these together and I'll write that number down and I'll draw a line, then I'll multiply these together and write that number under it, and then I re-enter things. If you know how to enter these into it's not that hard to enter them all in at one time. I tend to make more entry mistakes when I do it that way. I'm not real good at running those scientific calculators, so that's what I do. Feel free to do it either way. So I'm going to pause this video while I do this, okay? I hope. So, CEA, I did my calculations. I hope you did yours. I did mine. I decided to go ahead and do it. This was way easier. I did it on my computer and I just typed in scientific calculator into Google and it brings this up. Here's how I did it. I put my open parentheses 10.44 times the length of pipe that we figured out, 16,565.3 times 100 to the 1.85. Then I close my parentheses, divide that by 100 to the 1.85 times 8 to the 4.8655, close parentheses. And it comes up with this. And I've done this before. This looks correct. So that's how I typed it in there. Um, to get the exponent, I just typed the number, so 100, and then I hit x to the y and hit 1.85, and it types it in there just like that for you. So anyway, this is my answer. I rounded the nearest second place after the decimal. So going back to my page, I get HF. So my losses are after, so I figured out all this to get this number to plug into this formula, and I take, numbers from the scenario they give me and I plug them all in here and I get 6.98 feet of water. I'm going to lose that due to friction. So down here on my dynamic head, I take what was my static head, 109.81, and I subtract out my 6.98, and I will get my the the pressure of water after I subtract out for friction. So 109.81 minus 6.98, and I come up with 102.83. Now, this is feet of water. I can't say this enough. So that is our dynamic head. But nobody really refers to the pressure in your water pipes by feet of water, right? And what does that equal? Well, if we went back to our thing here, there was a slide up here that I showed you that talked about for every 2.31 feet of water, you're going to get 1 psi. Okay. So if I go back down here, D is going to be, if I go back to my, uh, how do I do this? I'm going to shrink this. Lord, I'm having trouble. I want to come here. So if I shrink that down, D on here is going to be calculate the actual pressure in front of the house. Then it asks, is the pressure sufficient for residential use? And I'll talk about that in a second. So figure out the actual pressure. Well, using this slide, I'm going to divide what I got here in feet of water, find pressure in PSI. So I take my 102.83 and I divide it by 2.31 because for every 2.31 feet of water, I get 1 psi. So I just divide these out. So divided by 2.31, and I get 44.52 psi. So I'm going to have 44.52 pounds per square inch of pressure, 6 feet below 10th Street, um, which is what they asked me. So the question then is that a good pressure? So we're now going to go E. Does that work? And then we're going to do that, we're going to have to come back over here. We also when I went through this presentation, they say in a residential setting, the minimum distribution pressure should be 40 psi, maximum 80. So if you're over 80, you got to put a pressure reducing valve in. If it's below 40, the city should have to remedy getting that up to 40. Or you might have to put a pressure tank in your house to fill a tank. Anyway, we'll talk about that another time. So we're going to say yes, this is within normal PSI range for residential setting. So that answers that. So what you're going to do next is you're going to go back to here, and they just have you do another scenario. It's done exactly the same way. The only difference is they give you a few more of these fittings that you got to look up on that chart and give equivalents to and add in. But that's really the only difference. Everything else on here is pretty much the same thing. So I want you to go through and finish that and do that. I will probably come on and walk through what I did. I'll make another video talking about this so that you can look at that as well. But this is what it is. We'll take a quiz over over being able to do this um, after we've practiced it a couple times. So that is figuring out your water pressure using static and dynamic head and converting to PSI. All right, guys. Um, until next time.